Let's look again at our system of a pool ball on a pool table. If we define the system as the ball, the raised edge of the table, and the side of the table, then to represent the moment of impact, if we were to draw arrows of all the forces acting on each of these components, it would look like this. We would have one arrow representing the ball hitting the cushion. So the ball exerts a force on the cushion. And of course, according to Newton's third law, if the ball exerts a force on the cushion exerts a force back on the ball. Likewise, since the cushion is being pushed against the side of the table, the cushion exerts a force on the side of the table, and the side of the table pushes back on the cushion. Note that this is not a free body diagram. We have drawn free body diagrams in the past, but this is not a free body diagram. Remember, a free body diagram needs to show one object and all the forces that act on that object. So this is just a visual representation to help us define what forces are going to be acting on each of these three components. This is not an isolated system. If we wanted to define an isolated system, we would have to have a system that includes the table surface. So we would have to show the ball exerting a force on the table exerting a force back on the ball. If we look at this example of two girls on roller skates pushing against each other, the girl in the red will exert a force on the girl in the yellow shirt, and the girl in the yellow shirt will exert a force back on the girl in the red sweatshirt. But they will both exert forces, so an equal force will be exerted on each girl. Now, will they move the same? Will they accelerate at the same rate? Will they move the same distance? Will they move at the same speed? And the answer, of course, is no, because of Newton's second law of motion. Remember, Newton's second law of motion says force equals mass times acceleration. So unless these girls are both the exact same mass, they won't accelerate at the same rate, even when the same force is applied on both of them. One thing that's useful for determining the speed at which they move, one law, is the law of conservation of momentum. Remember, the momentum of any object is mass times velocity. So each of these girls has her own momentum. Before they push off of each other, or their initial momentum, P sub I, their total momentum is zero. And each individual person's momentum is also zero. Why? Because they're not moving. Remember, momentum is mass times velocity. So if their velocity is zero, then their momentum is also zero. Now, after they push off of each other, then their total momentum is going to be m1v1, that's the mass of the first girl times her velocity, plus m2v2, the mass of the second girl times her velocity. The question is, are P sub I, the initial velocity, the initial momentum, and the final momentum equal to each other? And the answer is yes, because the momentum of the first girl is equal and opposite to the momentum of the second girl. Remember, momentum is a vector quantity, and since our velocities are in opposite directions, then one is equal to the negative of the other. And when you add a number to the negative of itself, you end up with zero. So the total momentum after they push off of each other is still zero. And this is true in any case. If you had an object that was exploding into several pieces, if you added up the momenta of all of those pieces, they would add up to 0. Let's look at this situation where the white ball crashes into the red ball. If the white ball collides with the stationary red ball, what is the most likely result? The most likely result is that the white ball will stop and the red ball will move to the right. The white ball is moving, so it has momentum. The red ball is stationary, so it has no momentum. When they collide, the momentum transfers from the white ball to the red ball. Now, if you have ever played pool, then you may know that you can change these variables a lot by taking advantage of friction. So you can put spin on the balls to cause them so that they don't hit each other directly. They don't act as frictionless objects. But if we ignore friction here, as we often do, then the white ball will likely become stationary and the red ball will continue to the right. If both balls are the same mass, then the red ball will continue to the right at the same velocity that the white ball had right before it hit the red ball. If they're different masses, then they will not have the same velocity. So we can summarize this in one equation, m1 v1, the momentum of object 1 before the collision. So v1 is, or it doesn't have to be a collision. In the case of the two girls pushing off of each other, it was an interaction. But the momentum of the first object before the interaction plus the momentum of the second object before the interaction, so that's v1 for both of them, is equal to the total momentum after the interaction. m1 v2 is the momentum of the second object after the interaction or collision, and m2 v2 is the momentum of the second object after the interaction or collision. So the total momentum before the interaction is equal to the total momentum after the interaction. So let's look at the challenge question. Describe when you can use conservation of momentum to determine the final conditions of objects involved in a collision. How can you use conservation of momentum to analyze the momentum of a rocket before and after launch? Remember, the launching rocket was our investigative phenomenon for this lesson. Well, according to the law of conservation of momentum, momentum is always conserved, just as total energy is always conserved. So those are two separate laws, conservation of momentum and conservation of energy. The law of conservation of momentum, it's simply a statement of Newton's third law. Remember, Newton's third law says that every action has an equal and opposite reaction. The equation of conservation of momentum can always be used, but it contains two unknowns in this case. We don't know the final velocities of the two objects after the collision. When you have an equation with two unknowns, it is difficult to solve. You need to make one of those unknowns known. We can use an extra equation with the same unknowns to solve for the final velocities of the objects. And if this is an elastic collision, in other words, if it's a collision where the two objects collide with each other, they interact with each other without losing any energy, then we can use the equation for kinetic energy to find the final velocity. Remember, the equation for kinetic energy is kinetic energy equals 1/2 mv squared. So it's using the same variables as the law of conservation of energy. For a rocket, the momentum before launch is equal to 0, right? The rocket is just sitting on a launch pad, so it has no momentum. After launch, the gas expelled from the engine has momentum. From the law of conservation of momentum, the gas is what's pushing the gas being pushed out of the rocket is an action force, and then the gas pushing the rocket up is a reaction force, or the other way around, if you like. But after launch, the gas expelled has momentum, and from the law of conservation of momentum, the momentum of the rocket at any given time will be equal and opposite to the momentum of the gas it has expelled. By knowing how fuel burns, engineers can project the speed of the rocket at any given point in its liftoff just by knowing how much fuel remains.